with a video today about your notes on 6.6, which is nuclear energy. So we have a lot to do with these notes. We'll try to get through it as efficiently as possible. But the first thing I want to do is look over these two energy diagrams that you see here. We have one that kind of looks like an outline of a power plant. So we want to know what's happening at each of these things. And the bottom one that is labeled geology of fracking, we're looking at where do some of these energy sources that we've talked about, where are we obtaining them from and how are we getting them, okay? So as far as the energy diagrams go, you'll need to be able to label the major parts of these. So we'll take a few minutes to do that. Now, I know this looks very overwhelming. Please don't freak out. All right. What I really care about you knowing is what's happening here. All right, we have combustion here in this first square. This would be your boiler or furnace. The combustion is being fueled by either coal, oil, or natural gas, which is a hydrocarbon. All right, the furnace or boiler will have a smokestack attached to it. This smokestack directs all these other thingies that are produced during combustion out into the atmosphere. And this could include things like carbon dioxide, carbon monoxide, sulfur dioxide, and particulate matter. That's what PM stands for. All right. Now, why do we do this combustion? Well, what we're trying to do is we're taking that chemical energy, we are transforming it into heat energy, where we're boiling water in this kind of like squiggly line. So this squiggly line you can add on to it. Now, why do I need that water boiled? Well, I need it to turn into steam. Steam has kinetic energy, and I'm going to have a turbine in this second box. So you can draw something that looks kind of like this, where you have like these kind of little like fan type thingies. All right. Why do I need a turbine spinning? Well, that turbine spinning is attached to a generator. And a generator, all right, when a turbine spins, it's going to spin a magnet around a copper coil in the generator. And that's going to create a flow of electrons out to the transformer, which is going to distribute that electrical current to homes and businesses in the electrical grid. All right, now that steam doesn't just stay here in the turbine forever and ever. It's going to go back down. It's going to be cooled off in a cooling tower. All right. That water that is a result of that condensation can either be recycled back to the boiler or furnace, or it can be put back basically where it came from, like a cooling pond. All right, so this is why a lot of fossil fuel plants will be near bodies of water like lakes or rivers. Because they need access to water to create this steam in order to get this turbine to spin, in order to get this generator to run. All right. Now let's look at where some of these fossil fuels come from. Just a quick review. All right, so here we see this diagram. So what could this be? Well, these are, I know it's kind of hard to tell what this is. This is an oil derrick. So we have oil, and this is presumptively natural gas, because oil and natural gas are often found together. All right. So here's what we're looking at. What I need you to remember from this, what I need you to take away from this, is a lot of oil and natural gas drilling operations will have to go through aquifers. They will have to drill through those, which is a point where it can potentially become contaminated. Okay. Your deposits of oil are going to be under these layers of sedimentary rock. And if you have a porous but impermeable layer above the oil, you will trap the natural gas there. You will trap that natural gas as it tries to float above. If it doesn't have an impermeable layer above it, this oil and natural gas can naturally rise up to the surface, and that's what makes tar sands. All right. Now, what happens when we want to access natural gas in another way? Well, what we can do, we can use a fracking operation, which remember stands for hydraulic fracturing. So you drill down again through the aquifers, through the different layers of rock. down to your layers of shale, which are going to have your natural gas trapped there. You're going to put in water or other chemicals in this well in order to cause it to fracture or break. You basically cause little mini explosions. That is going to break the rock apart and allow that natural gas that is trapped in that rock to flow up and out of the well. Okay? So, enough about fossil fuel energy. Again, if you need to go back and look at those diagrams, feel free to go back and pause those videos. So nuclear energy, we have a lot to cover with this. These are all of our things we need to get through. We want to know how electricity is generated through nuclear power. We want to know what radioactivity is, and how we can calculate radioactivity and how that impacts the disposal of nuclear waste. We want to know if it's renewable, non-renewable. We want to know some of its pros and cons. And we want to know some of the historical kind of big examples of nuclear energy not necessarily going the way we want it to. All right, so you'll be expected to know these 3 specific examples. All right, so let's start with this chart that you have in your notes comparing nuclear fusion to nuclear fission. So nuclear fusion takes place where you have little nuclei like hydrogens, and they fuse together, hence its name, to make a larger atom like helium. All right, this normally only occurs really in stars. Stars are so massive, they have such high amounts of gravity. You can get enough heat and pressure in stars to force little hydrogen atoms together. Normally, they don't like to be near one another because their protons will repel each other. Now, during this process, all right, we remember Einstein's E equals mc squared. All right, mass can be converted to energy. All right, some of the mass, all right, from these 2 little hydrogens, they get smushed together. Some of that mass is converted to energy, which is usually in the form of heat and light. So heat and light, either UV, visible, or infrared. Now, on Earth, fusion is not really super practical right now because we can't figure out a way to get atoms to fuse in any sort of meaningful way. We can get fusion to happen, but it's either only for little itty bitty blips at a time, so like the amount of energy you're getting out of it is not worth it, or we have like uncontrolled fusion reactions like in hydrogen bombs, which is obviously not something we want to deal with, or not necessarily great either. All right. Fission, on the other hand, this is what we do on, this is what we are good at on Earth. Fission happens when you break an atom down into smaller ones. So you take something great big like uranium or plutonium and you bombard it or smash it with little neutrons and it breaks it apart. All right. This is also, like fusion, going to release a ton of energy. And that energy can be converted into electricity, much like the chemical energy of fossil fuels can be converted into electricity. All right. Oftentimes, now on Earth, we have gotten really good at figuring out how to induce a fission chain reaction. So once we start fission, we can get it to keep going. And fortunately for us, we can do this in a more controlled manner, which is going to be very practical for us when we're trying to make electricity. Okay, a little bit about nuclear energy in the U.S. 20% of our electricity currently comes from nuclear energy, so about 1/5, so a good little chunk. And the neat thing about nuclear power plants, they work the exact same way as fossil fuel ones. We are releasing that energy, all right, that heat that is being, that heat energy from the fission reaction is used to heat water to make steam, and this kinetic energy from the steam turns the turbine, and that rotational energy is connected to a generator, and that generator can spin or that the magnets in the generator can spin around the copper coil, and now you have electricity. Now, the nifty thing about nuclear power and nuclear fuel, 1 gram of uranium-235. If you ever see an element like this with a number, that's just its isotope. That's how many protons plus neutrons it has. So like the bigger the number, the bigger the atom. 1 gram of uranium-235, which is a very common nuclear fuel, has 2 to 3 million times of energy as 1 gram of coal. So it's super, super energy dense. 1 pellet of uranium, which is about 7 grams. So think about how much 7 grams weighs, not a lot. Can make as much energy as 3.5 barrels of oil, almost a ton of coal, and 17,000 cubic feet of natural gas. So you need way less stuff to get the same amount of energy, which is awesome. All right, so here's that fission reaction we were talking about. Let's take a look at it. We like pictures here. So really big atoms like uranium-235 and plutonium, they're already very unstable because they are so large. The protons don't like to stick together. It takes a lot for that atom to kind of exist, and it will break down eventually. Here's our neutron. We are splitting it apart, and we can see what we were talking about with the chain reactions. All right, these neutrons run into other bigger other atoms and split them further and further and further down. All right, this is why like nuclear weapons are so powerful. Again, you can get a lot of energy going or a lot of energy released very, very quickly. Why nuclear power plants are so efficient. You can get a lot of energy going pretty quickly. Now, fortunately for us, with nuclear fission and in power plants, there are ways to control these reactions, which we'll look at here in a minute. Okay, let's talk about radioactivity for a second. So some critics of using nuclear energy may reference radioactivity, that we are using radioactive elements, which is 100% true. All right, radioactivity is, what that is just energy in different forms. So you can have alpha particles, beta particles, gamma particles that occur when that nucleus breaks down over time. So radioactive elements will break down eventually on their own because they are so unstable, but nuclear fission just makes that process happen faster. All right, we measure radioactivity, or we can look at how long something's going to be radioactive for by looking at its half-life. All right, so we're going to have a little bit of math here, not a ton though, nothing you need to worry about. But a half-life is just what it sounds like. It's how long it takes for 50% of your radioactive stuff to break down. So here we have an example, cobalt-60, that's the isotope, has a half-life of 5.27 years. So in 5.27 years, half of your cobalt-60 will be gone. It won't be cobalt-60 anymore. It'll be something else. So if you started off with 500 grams of cobalt-60, in a little over 5 years, you'll have 250 grams. And in another 5 years, you'll have about 125 grams. And in another 5 years, you'll have about, 70 some odd grams. All right, or 60 some odd grams. You'll never completely get rid of it. You'll just get very close to zero. Okay, so we can look at half-life in a couple different ways. We can look at half-life on a graph like this. Boop. Here we go. All right, so at 0 half-lives at the beginning, you'll have 100% of your sample. After 1 half-life, you'll have about 50%. 2 half-lives, about 25%, so on and so forth until you get these itty-bitty numbers. So using this graph, we can kind of figure out how long will it take for me to get 40% of a sample or 10%. Well, I just go to my axis, percent of original mass remaining. There's 40. I go over to the line. It's a little past 1 half-life, but not quite 2. Not quite 1.5 either. So I'm going to say 1.3. To get 10% of a sample, again, 10%, I'm going to go over to the line. It's a little past 3 half-lives, so it's been cut in half at least 3 times, but not quite 4. All right, you can see there's your potential answers there. Now we can also look at it in a table format. So we have osmium-183, again that's the isotope, We have a half-life of 12 hours, 12.0 hours. Complete the table for the initial sample of 180 grams. So you have a table in your notes. All right. At 0 hours, I have 180 grams. Well, how much will I have after 12 hours? Well, I should have half of whatever 180 is, because 12 hours is how long it takes for half of this to decay away. So you end up something with looks like this. All right, so 180 gets cut down to 90. 90 gets cut in half to 45. 45 gets cut in half to 22.5, so on and so forth. Basically, I'm just dividing by 2 for each half-life. All right. And if you want to be extra about it, there is an equation for all my friends who are like, well, I've taken Math 3 and I've learned about exponential decay. That's really cool. Good for you. All right, here's what it is. All right, it's your original mass times 1/2, all right, raised to time over half-life time. So let's say you have, all right, we have the half-life of cesium-129. We have a 65-gram sample. It's going to take 56.3 hours to ship between laboratories. How much cesium-129 would be delivered? So we have the original mass, 65, times by 1/2, raised to 56.3 divided by 32.1. All right, and you should have something that looks like that. All right, now you're like, well, what if I just have a regular schmegular calculator and I don't have the fancy exponent feature or whatever? Well, you don't need the exponent feature. You don't need that exponent feature. You can do something as simple as this. All right, so here we have radon has a half-life of 3.8 days. After 7.6 days, 6 grams remain. What was the original mass? Well, first thing I'm going to do is I'm going to calculate how many half-lives do I have? So I would do 7.6 divided by 3.8. All right, that means there's 2 half-lives, which means my sample got cut in half twice. So now I just work backwards. And it's going to look something like this. All right, so 6, that's how many I had at the end. Well, that was 12 originally, which was 24, all right? Each of these arrows represents a half-life. All right. And we have our last problem. Again, you can use a calculator if you want, but you really don't need to. Radioactivity level of 100. We have radioactivity level of 100 curies. A curie is just a measurement of radioactivity. I don't need you to know what that is exactly. It's not an element. It's just how much radioactivity we have. We have a half-life of 50 years. What will the radioactivity be in 200 years? Well, how many lives do I have? 200 divided by 50 is 4 half-lives. So I'm going to cut 100 in half 4 times. Not 100 divided by 4. 100 cut in half 4 times. So I would go 100, all right, then 50, then 25, 12.5, 6.25. All right, you can also plug it in this way. You can also plug it in this way in that fancy formula we did. I'm personally a really big fan of just cutting things in half. All right, so I don't have to worry about, did I put my exponents in right? Did I raise things to the right power? I'm a big fan of half-life, cut in half, cut in half, cut in half. Okay? Awesome sauce. So that is the extent of the math that you'll need to know specifically for half-life. Now, how do we get uranium? How do we obtain uranium? Where does it come from? And what are the consequences of that? So the nice thing is that it is a not super uncommon element. So uranium is going to be found with some relative abundance in Earth's crust, which is kind of snazzy. You can find it in most rocks, ocean water, rivers, whatever. We are going to extract it by mining. Now, that means we're going to have all the effects of mining, but remember what we said earlier, I don't need a lot of uranium to make a lot of energy or to generate a bunch of electricity. So you kind of minimize the effects there. Uranium mines are can be found in a lot of places, but most uranium is produced in these 6 countries. So you have Kazakhstan, Canada, Australia, Namibia, Nigeria, and Russia. Okay, obviously we know with like current geopolitical states right now, how they are, like that can be a problem, all right, if one country decides, hey, I have all these resources, but I'm not going to share with anybody, all right, because of the current geopolitical climate. Now, in order to make uranium usable, unlike coal, all right, coal, you can take it out of the ground, you send it to the power plant, and you combust it as is. In order to make uranium useful in a power plant, you have to go through a refining process and an enrichment process. And that is very time consuming and very costly. And that is going to be another kind of like drawback to using uranium. All right, once we have refined this uranium, okay, once I've done that, how do I make the electricity? Again, like I've said before, it's very similar to how we do that with fossil fuels. It's just instead of using combustion, we are using fission. Do not say, we do not burn uranium. That is not a thing that is done. Don't say that. Okay? Uranium is broken down through nuclear fission, and that release of heat is what makes the water into steam. Steam turns the turbine runs the generator makes electricity. Again, this is kind of like the central part of your answer for your FRQ. I'm going to ask you, how does X make electricity? This is the kind of order that you need to remember for most of the energy sources. So, uranium-235, we're going to have these in fuel rods. They're going to be submerged in water in the reactor core. Now, this water that's in the reactor core is not the actual water that eventually turns into steam. That's something slightly different. We'll look at that in our little diagram here in just a minute. But the fuel rods are where the fuel is, obviously. And then we have the control rods. Like I said earlier, with nuclear fission, we have figured out a way where we can stop that chain reaction if we want to. So the control rods can be put between the fuel rods, and it can absorb the neutrons so they don't run into other uranium atoms, which can slow down the fission reaction if you're getting too much heat, if you're getting too much, if that chain reaction is starting to get out of control. And this is helpful in preventing nuclear meltdown. A lot of times with the nuclear accidents, which we'll see, there's something wrong with the control rods. There's something wrong, and that chain reaction just kept going and going and going until there was too much. Okay, whoops. All right. Let's see, do I need you to write anything down here? Yeah, I do actually, so I'll give you a second to write that. So we have fissioning happen, and again, we'll look at this diagram that you have on your paper. So fission's happening in the reactor core. It's kind of the heart of the nuclear power plant, where fuel rods are submerged in water. The control rods can be put in between the fuel rods to regulate the reaction rate. That water that is heated in the reactor is pumped through a pressurized primary loop. Now, the primary loop goes to a secondary loop, all right? And that water in the secondary loop is the one that actually gets boiled or gets created into steam that can then be used to turn the turbine. The steam turns the turbine, which is then used to spin or rotate the magnets in the copper coils in the generator, and then you have the electricity. Now, the water in the secondary loop, all right, is going to go through a condensing tower or a cooling tower. It's going to convert it back to liquid water, which can then be brought back for it to be boiled again by the primary loop. So what that looks like is this. So you have this on your paper, okay? So really the only difference here is this water, this like dark blue, this is not the water that actually like spins the turbine. It's this lighter blue water. In the secondary, this is the secondary loop, the steam generator. All right. This water is just conducting this water in the primary loop is conducting the heat from that fission reaction. Sometimes they'll use what's called heavy water coolant, and what heavy water is just water that's enriched with a particular form of hydrogen. Again, not really super relevant, but that's why it's different. All right. So steam goes out, turns the turbine, powers the generator, everyone's happy. The steam gets condensed and brought back through that secondary loop. All right. Now water, just like the fossil fuel plants, all right, nuclear power plants are always going to be on a body of water because they're constantly having to bring water in to help condense the steam back to liquid water, all right, and help take some of this excess heat out, all right, which generates its own problem. So, what are some of the benefits and drawbacks of nuclear energy? So, nuclear energy, contrary to, this is kind of weird, nuclear is non-renewable. All right, there's only so much uranium on Earth. There is a finite supply of uranium. We can eventually run out. Okay, but just because it's non-renewable doesn't mean you get the same pollution that you get with other fossil fuels. So because there's no combustion happening, there's no air pollutants, so that means you're not going to get any of that particulate matter, sulfur dioxide, all right, nitrous oxides, carbon dioxide, methanes, carbon monoxide. Okay, the air around that is going to be free of any of those pollutants. So that is a phenomenal benefit to nuclear energy. But there is a possibility that something awful goes wrong, something catastrophic happens, and you have this possibility of meltdown and radioactive contamination. Now, the neat thing, or the nice thing about this, is this possibility is extremely rare. Okay, like this does not happen all the time. It is very unusual for like a full meltdown to happen. It is very, very unusual. It's very, very rare. And that is because nuclear energy plants are built to such high safety standards. You put a ton of money in up front to build in these safety nets so that that is unlikely to happen. All right. Now, other things you got to consider, the fuel rods, they got to go somewhere. All right. The half-life of uranium, all right, and these radioactive elements can be tens of thousands of years, so they're going to stay radioactive, and they need to go somewhere. I believe all of the fuel rods that are currently used in the United States, I believe they all end up eventually in New Mexico. But you can imagine, if you lived in New Mexico, you'd be like, well, wait a minute, is that dangerous? And the answer is kind of yes, it is. All right, nuclear power plants are going to need a lot of water. All right, to generate steam, they're going to need a lot of water because, again, you're getting a ton of heat from each fission reaction, so you need a lot of water to make sure that you have, you don't end up, like, melting your reactors. And that's going to result in thermal pollution. So some of the water that comes out, all right, here, this water that goes back out, all right, it's carrying some of this heat with it. All right, remember, like heat is a form of energy. It doesn't magically go away. It's got to go somewhere. All right, so that goes back into the surface waters and can cause what's called thermal shock. Basically, your water is a little too warm, which means you have less oxygen because you remember, warmer water equals less dissolved gases, and that's going to negatively impact your biodiversity. All right. So here is a nice little slide that has all of our advantages and disadvantages. Again, we've talked about most of them. We've talked about most of these already, but if you want to just jot them down in bullet point form. The only one we didn't already talk about, nuclear energy is very predictable. It has a very high capacity factor. You can run nuclear power plants pretty much over 90% of the time, and you know exactly how much energy you're going to get out of it, which is very nice. Again, like we said, there's a very low risk of accidents because it is so regulated. There is so much investment up front to prevent that. and I don't need as much land disruption like I would for like a hydroelectric dam, or like a fossil fuel plant where I have to mine and I have to disrupt quite a bit of land to get enough fuel source. All right, don't have that. All right. Now the mining process is going to produce pollution, waste, runoff, land damage. There are some nuclear accidents. We are going to talk about 3 notable ones. Even though they are very rare, when they do happen, they are quite spectacular. Concerns over how to decommission old nuclear power plants. So once I'm done with it, how do I shut it down safely? How do I do that? And then fear of natural disasters near power plants, nuclear power plants. Again, we'll look at that with one of our 3 notable examples. So let's take a look at some of our notable examples. All right, so let's take a look here. This one happened in the United States, 3 Mile Island. It's in Pennsylvania, if you're not familiar with this already. It happened in 1979. You do need to know like where and kind of like the general like what happened. So in 3 Mile Island, you had a cooling water valve that was closed. All right, so you weren't able to condense that steam back down. This lack of cooling water around the core, that core got too hot, led to a partial meltdown. They did evacuate over 200,000 people. There were no reported immediate like deaths directly attributed to this. However, around the area afterwards, we do see an increase in infant mortality and rates of particular cancers. All right, now we all know that correlation is not necessarily causation, but it does raise the question, did this partial meltdown lead to a change in human health? And it's very plausible. It's 100% plausible. All right, our next nuclear accident that you are probably a little more familiar with is Chernobyl in what is now Ukraine. Back then, it was part of the former Soviet Union in 1986. This actually happened. This is a really interesting story. It's been very well documented. There's a lot of really good like TV shows about it and stuff. You can look into it. But this happened during an evening test. It was in the middle of the night at like 2 a.m. or something like that. And basically what they were doing is they were testing what would happen if we ran out of power, we being the nuclear power plant. So they're like, what would happen if we weren't able to move the control rods? And what ended up happening is kind of what you would expect is it overheated. Now, unfortunately, because this was a nighttime test, why did they test it at nighttime? Well, people aren't using as much energy. Okay, that checks out. But who works at nighttime? Who works the third shift? It's your junior scientists, your people who are brand new to the job, who have not worked their way up the ranks yet. So they were very inexperienced. So this test really got out of their hands. You had a massive explosion in reactor 4. All right. At least 31 people died at the time. I think there were like 2 plant workers that died in like the actual explosion itself. Like they were trying to prevent it from getting to other reactors. And then 20 some odd like rescue workers, firefighters, things like that. Many of them died from acute radiation poisoning. All right. Now in Ukraine, around Belarus, what we have seen in the almost 40 years since this has occurred, is that cancer deaths have greatly increased. All right. The numbers of people being born with really, really, really severe birth defects have increased. And we're like, well, what is that from? Well, there's a very good chance that this radiation that was released during this explosion, all right, caused mutations that ultimately led to this. Now my favorite part about this story, all right, this is 1986. This is the height of the Cold War, right? This is like, people are on edge, right? About nuclear weapons and like what the Soviets are doing, what the Americans are doing, all this mess, all right? This radiation did not stay contained around Chernobyl, around Pripyat, Ukraine. All right, it spread all over Europe. And the rest of the world didn't actually know about this event until like 2 or 3 days after it happened. Because the Soviets, of course, back in 1986, they're trying to like be the dominant world power, they're not going to tell the world that, like, hey, one of our power plants blew up. They're not going to do that. That would be silly. So it's not until like 3 days after it happened that scientists in Sweden start measuring these like super high levels of radiation, and like a red flag goes up and they're like, we think somebody dropped a nuclear weapon. We think somebody just tested a nuclear bomb or dropped a nuclear bomb somewhere. Who did it? And they were like looking at the Soviets, looking at the Americans, looking at the Soviets. And that's when like the Soviets were like, yeah, that was us. Sorry, guys. And they try to like minimize it to the best of their ability. But obviously, like, it has never fully, like, around Chernobyl is still highly radioactive. The soil is highly radioactive. It's getting to the point where we can't kind of go in and study. We can look at like the effects of the biodiversity. And what we're seeing is like a lot of the organisms that live around this area have been negatively impacted by this exposure to radioactivity. Right, and our third nuclear accident that you should definitely be familiar with is the Fukushima Daiichi disaster of 2011. This is what I was talking about with natural disasters. So this happened in March 1st, March 9th, 2011, very recently, had the anniversary of it. You had a 9.0 earthquake off the coast of Japan, which again is not really that out there for Japan. That's pretty typical. Not typical. 9.0s are pretty unusual, but still, Japan lies at the convergence of 3 plate boundaries. All right, this triggered a 15-meter tsunami. So you had major flooding, and it flooded this power plant, Fukushima Daiichi. Now, this flooding basically shut down the power supply that was bringing water in to help cool the reactors. Now, of course, being in Japan, they're very earthquake aware. They know that these things are going to happen. So they were like, so there was a backup plan, and the backup plan was there were battery packs that would help bring water in to cool the reactors or whatnot. But the battery packs had a limited lifespan. They were only going to be good for like 8 hours or something like that. So eventually you did have fires, you did have explosions, and you did have a release of radioactive material. Out of 6 reactors, 4 were destroyed. 100,000 people were immediately evacuated. All right. But we had this massive release of radioactive material into the Pacific Ocean, the world's largest ocean basin, and it has spread throughout the ocean basin. And it's only been, not quite, it's been about 13 years. We don't know the full extent of what this radioactivity is going to do to ocean ecosystems, or the ecosystems surrounding Fukushima. All right. So again, you do need to know those 3. You are expected to know those 3 examples, kind of like where they happened, when they happened, and what the results were. All right. So I'm going to leave y'all with some practice FRQ questions. We have a diagram of a nuclear power plant that's been kind of simplified down for you. You're going to identify and describe a letter that is common to both nuclear and fossil fuels. So what could I find in a coal power plant that I also find here? And then you're going to identify and describe a letter that I only find in nuclear power plants that I would not find in a fossil fuel power plant. All right. So I'm going to wrap that up. I will check these later, and we will continue this discussion tomorrow.